noise in the background, right?
Just cannot, you want to talk, please.
So yeah, so let me, first of all, I'm going to acknowledge some of my students who have contributed, to the work that we do in my lab at Georgia State University, and that includes Sushma Dahal, who just completed a postdoctoral fellowship at the Center for Disease Control, Amanda Blakerod, who finished her PhD at Georgia State this year, and now she's a postdoc at Clemson University doing epidemic forecasting and coordinating centers of epidemic forecasting in the United States. I have a student, Hamed Karami, who is a PhD student. He is based in the Department of Mathematics and as well as the School of Public Health. And he's combining hard mathematics with public health to improve methodologies and develop toolboxes for epidemic forecasting. And then finally, Yuganti, who was a PhD student at Florida Atlantic University, and she collaborated with me because I collaborate with her PhD mentor, Najibe Tuncer. And now she's a postdoc at Arizona State University. So let me mention some of them. I would say the hot research areas in the field of epidemic forecasting. So that includes, developing novel ensemble techniques. So different ways of combining forecasts from multiple models with the goal of improving the prediction ability of systems. And so that's a major research area right nowadays. There's a lot of work being done in that area in the last few years. And yeah, we have contributed in that field. Then we have developing multi-scale models at different spatial scales, resolutions that combine commuting data, flight data, transportation data, with the goal of, again, improving our ability of forecasting as well as inferring key transmission parameters. Then other areas include identifiability analysis, which is the one that I will be emphasizing during my talk. As you know, identifiability analysis is very important because it is critical to know if a parameter can be estimated from the data, from the observables that are available. And so having methods to be able to conduct identifiability analysis is crucial. And a major area in this field is quite mathematical. So looking for better approaches, more efficient approaches that can work with more complex models, because sometimes the techniques that are available only work with low to medium complexity models. And finally, obviously machine learning and AI is a big hotspot, important area of research now that AI is exponentiating our ability to use large data sets to train models and improve predictions, combining artificial intelligence techniques with classical approaches, OD models, mechanistic and phenomenological models, can really improve our ability. So the work that has been done in that field has shown quite a bit of promise. So the first thing that I will emphasize is the fact that when we conduct forecasts, right, we typically focus on the OD system. So, whether the model is mechanistic or semi-mechanistic, we focus on that and less on the type of error structure, because there is some assumption about the error structure in the observables, whether that's incidence, number of hospitalizations or deaths. we are always assuming something such as normality in the error structure or Poisson or negative binomial. So it is important to clarify which error structure is being assumed. And that's sometimes that's lacking and needs to be accounted for. So that's one of the research areas that we have been working on, highlighting the fact that if the model assumes different error structures, the forecasting performance can vary substantially. So in this slide, I'm showing you a very simple example that compares the performance of the SCIR model, which you know very well, and the generalized logistic growth model, which is phenomenological, and is summarizing the average performance in these bar plots on the right. So you can see that the performance of the models vary in terms of the mean absolute error or the mean square error or the coverage of the 95% prediction interval or the weight interval score. The performance actually depends substantially on the type of error structure. And the error is actually lowest in this example when we use the negative binomial error structure. So it's emphasizing that it's not only about the mechanistic, the model, the ODE system, but also about the assumptions of the errors. Another very important aspect in forecasting when we use no models for forecasting is parameter identifiability, because when we conduct forecasts, we need to create the model first. We need to track with data. It is very important that when we do that training and the parameter estimation, that the parameters can be actually estimated from the data, because it's not always possible to estimate a parameter from a given data set, from a given observable, right? So in the literature, it is great to see that our interest and our emphasis on practical and structural identifiability, as you can see in this figure, has been increasing, shows the trend in the number of publications that includes structural identifiability or practical identifiability or both. So especially after the H1N1 influenza pandemic of 2009, we see an increasing trend in the number of publications that account for this analysis. And I will be delving more deeply in the next few slides about exactly structural and practical identifiability. So here is a simple workflow diagram that shows some of the steps that we take when we fit models and when we use them for forecasting. And the shaded yellow area here highlights the fact that it is important. First of all, the first thing, once we have a model and once we have our data ready for fitting, it is important to check structural identifiability. Structural identifiability will tell us if a parameter can be estimated from the data, and is making a very, very strong assumption. Assumes that basically the observable is continuous, smooth, has no errors, and that we are observing basically the entire process, in this case, the entire epidemic, not only the early phase or not only the growth phase to the peak, but the entire process, meaning the entire epidemic curve. So that's important, because if the parameters are not structurally identifiable, then they will not be practically identifiable in practice. Once we assess identifiability with a specific data, with specific error structure or data type, if the parameters are not structurally identifiable, there is no point of doing practical identifiability, right? So you see here, we have structural identifiability, then we fit the model to the data. After we fit the model to the data, that means that the parameters are structurally identifiable. If they are not identifiable, then we need to either adjust the model, make changes, or maybe fix some of the parameters that are not identifiable, right? Then the quality of the model fit has to be assessed, right? That's the next step. Once you check the quality of the model fit and realize that the model is doing a good job in fitting the data, the next step is to check if the parameters are practically identifiable, right? So if they are practically identifiable, then we are good to go. We can actually use the model for forecasting, right? So this is the mathematical definition, right? So you are mathematician, so you understand this. This is this basically says that if a parameter is structurally identifiable, then there's only one solution. There's only one solution of the model that gives rise to the same set of solutions of the model. There's only one solution of the model. So that's indicated in this.
My own is not entrepreneurship. 101. That 101.
Can you hear me? Sorry, can you hear me? Hello. Okay, I'll continue. I'm sorry if you didn't hear me. Okay. So I was saying this is the mathematical definition of a structural identifiability, right? You have a parameter that is structurally identifiable. That means that there is a single unique solution of the model that gives rise to a single set of parameters. There's a one-to-one relationship. So there's only one solution of the model for a given set of parameters. Because if there is more than one solution of the model, right, or one set of parameters, then there is no mapping. And so we cannot really conclude, right? When we do inference, when we have data and inferred parameters, we cannot conclude something specific about the parameters because there may be other parameters of the model values, or the parameter values that gives you the same solution, right? So again, this is very important to be able to check that the parameters are mapping one-to-one to the model solutions. And in this regard, we have developed some tutorials to facilitate access to some of the tools for structural identifiability. So this on the left, you have a mathematical biology paper that we published last year. In mathematical biology, basically explains how to do it using DAISY software. The DAISY software was developed by Belu et al. And was published in 2007, and this is a use of software. And more recently, we did something relatively similar using a different software, using structural identifiability, which is a Julia package. Why did we do a second tutorial? Is because this new package, structural identifiability, which I recommend to you, is actually very useful when you have more complex models. Because the DAISY software doesn't work when you have more complex models, only for relatively simple models. So if you have more complex models with more boxes, more variables and parameters, structural identifiability will tend to work better. So I recommend that to you. So how do we conduct structural identifiability? Structural identifiability we conduct by, what do we need? We need a system of equations. We need the model equations, the system of differential equations. We need the vector of parameters of the model. We need to know if there are any initial conditions in the system that are known and which ones are not known. And then we have we can pass in that information to DAISY. We can get as output the structural identifiability results from the observations that are available to us. Another aspect is what variables are actually observable. What variables in the system, in the model, can we observe from the system, right? And the output,
It's muted.
so the output that we get again, sorry, the output that we get again is either the results are based on whether the initial conditions are known or not. When the initial conditions are known, it's more likely that the parameters will be structurally identifiable. Why? Because the initial conditions provide extra information. So the more information we provide, the more likely is that the parameters will be structurally identifiable. So let me give you some examples. This is the first example, is the SEIR model that you have used before, I'm sure. It's a simple model with just a few parameters, the transmission rate, the rate of exposure, the recovery rate, and the population size. And then in here, we assume that what we observe is the number of new infected cases over time. So the number of new infected cases given by kappa E, right? Because that's exactly the flow that goes from the E equation to the I. And you can see that better in this diagram, right? What's flowing from E to I is what we are observing, the incidence, number of new cases, all right? So notice that in this diagram, I'm indicating not only the system of equations as classically done with the boxes or circles and the flows, the arrows, but also indicating what we are observing. And that's included in this type of oval box with the dashed line. It's just to highlight what are we observing, because that's very important information to know. If we are observing only a few things, right, that will impact our ability to identify the parameters. So the results that you can see here on the left is without the initial conditions. If you don't know the initial conditions, everything is identifiable except for beta and n, right? Beta is the transmission rate and n is the population size. But we know n, right? We know the population size. So if we know n, we can know beta, because actually the parameter beta and n are correlated, as you can see here. And this is something that you can get from DAISY software. You can actually obtain from DAISY software what parameters are correlated.
Okay.
And if you know the initial conditions, right, all of the initial conditions, actually all of the parameters are identifiable. And this is what I just told you, right? If you have more information, if you know the initial conditions, then it's more likely that the parameters are structurally identifiable. And again, these results were obtained using DAISY software, right? The software that I mentioned to you in that we describe in this paper here. So one more example. In this example, it's a little bit more complex so that you see the differences, right? In this example, we have symptomatic and asymptomatic infections. So we have a few more parameters. You have rho, which is the fraction of exposed individuals that become symptomatic, and then the recovery rate gamma, right? And kappa is the rate at which the exposed individuals become infections. So in this model, we have one more parameter relative to the previous one, right? We have the rho. We need to differentiate what fraction are symptomatic, and then the asymptomatic is the complement, right? 1 minus rho. And then what we observe is kappa times rho times E. Why? Because rho is the proportion of symptomatics. The asymptomatics are not observed. So we are only observing a fraction, kappa times rho times E. And so if we do the identifiability analysis when we observe the incidence curve, which is given by this, you see that we get similar issues, that actually the parameter rho is not identifiable if we don't know the initial conditions, okay? That's a very important result. If we want to estimate the parameter rho, it's not going to be possible. However, if you know the initial conditions, the initial value of susceptibles, the initial value of exposed, sometimes we have that information, actually all of the parameters become identifiable, right? So it's important. If you have a model, it's probably the very first step is to check what parameters can be identified from the available observables. One more model. In this model now we have differentiated the transmission rate for symptomatic and asymptomatic individuals. So it's beta I and beta A, right? You can see here. So we are adding more complexity. So what happens in this example is that obviously now the beta for asymptomatic and for symptomatic are not identifiable just from the initial, the incidence curve alone is not possible. Why? Because there is a correlation, right? You see there are correlations. These expressions is correlation that indicates that beta I, rho, and beta A are correlated. And also there's a correlation between N and rho, the population size and rho. That one is not a problem because if we know N, we know rho, right? The good news is that if we know the initial conditions of the system, all of the parameters are identifiable. That's a good thing. Finally, one more example. In this example, we included mortality, right? So it's a simpler, except that now we have deaths. So we added the equation for DDDT, the mortality. And as you can see here, the incidence curve is given by this, right? And the results indicate that delta is not identifiable if the initial conditions are not known. That's important. Why? Because there's this correlation, this beta over delta correlation, as well as gamma plus delta. However, the initial conditions help us identify all of the parameters. So if we know the initial conditions, we can identify parameters. Now, one last example. In this last example, notice that we have two observables. In the previous examples, we only had the incidence curve. Now we have the incidence curve plus deaths. So we have two curves of information. Thanks to the additional observable, right? Thanks to that, all of the parameters are identifiable even without the initial conditions. Notice all of the parameters are identifiable. So this is saying, okay, even if I don't know the initial conditions, if I have information not only about incidents, but also about deaths, then I can identify all of the parameters of this model, okay? So as a way of, as a summary of this is that it's important to do structural identifiability prior to using the model to estimate parameters. More likely, the issues will arise when only a limited subset of the system are observed. So if we observe more variables in the model, well, more chances that we will identify the parameters. Knowing the initial conditions is good. It will help you identify parameters. So if you know the initial conditions, that will increase the chances of identifying parameters. And then incorporating prior knowledge, right, or fixing certain parameters can actually further assist in structural identifiability. So if we don't have identifiability and you know the value of the parameter from prior literature or prior experiments, etc., you could potentially fix it and do some sort of sensitivity analysis, right? So vary that parameter and see how the results are impacted. And then to connect to the next topic, important to say that even if the parameters are structurally identifiable, the next step is to check if they are practically identifiable, because practical identifiability arises from the real data. Up to this point, with the structural identifiability, we are not talking about the data yet. We are only talking about the structure of the model and what are the observables, right, that we are considering in the estimation of the parameter. Now that we consider the real data, the noise in the data, how much data is available, then we talk about practical identifiability. And as you know, for practical identifiability, you need to have a way of feeding the model to data, and you need code, right? You need MATLAB code or R code. And so we have developed some toolboxes to facilitate this process. Especially, we developed this Quanti Forecast Toolbox, and it's available in GitHub, that allows you to fit models, any type of ODE model, to the data. There's a tutorial paper and video and everything, lots of materials that can help in that regard. And more recently, with my student Hamed, we developed an Bayesian estimation approach for doing that, exactly that. But so as you know, with the Bayesian framework, you work with prior distributions. With the frequencies framework, you assume that the parameters are fixed, but they are influenced by some sort of randomness, right? Oh, yeah. Thank you. So let me tell you a little bit about these toolboxes and the methods that we use for that, for fitting, and then how they can be used for practical identifiability. So this is Quanti Forecast. The tutorial was published in Statistics Medicine. And then is my student Amanda Blaker is a co-author of that, as well as my colleague at Georgia State, Ruyan Luo. So basically, the workflow to use Quanti Forecast is divided in 4 sections. The first section is to specify the model and specify the data that you want to work with, right? You need a model and you need data. And then the next step is to test the model to be sure that the model equations were entered correctly. So there's a process of model testing. Once that you know everything is fine, then you can proceed to fit the model. Fitting the model means searching for the parameter estimates that gives you the best explanation of the data, the best quality fit of the data. And then generating and evaluating model-based forecast. Once you fit the model, you get a good fit, then you can generate a forecast. So you can do that here too. So you can fit the model and then you can use it to fit. But fit the model and then check that the parameters are practically identifiable. So I will give you a couple of examples. So the first step is to specify the system of the ordinary differential equations, ODEs, right? Which is something that you know. You do this all the time when you use your code in MATLAB or R. It's a set of equations, the rate of change equations. You need to specify the set of parameters, like a vector. And then importantly, you need to specify what variables in the model are connected to your data, right? Because that's the linkage that's going to define what's going to be optimized in terms of model observable. And then the rest of the states in the system are called latent states, which are not directly observed, but are inferred from the inference process. Okay. Then you need to specify the data set, right? You typically work with time series data. So you specify where is my data? It's a text file. You know, is it one column of data, or maybe you have multiple columns because you have multiple observables, you know, like incidence cases, deaths, or hospitalization. So you can specify that. Then the next process is the inference process. Parameter inference, as I was telling you, is the process of finding the parameter values that give you the best explanation of the data, right? And for that, there are 2 methods that can work with Quanti Forecast. Non-linear least squares, which is very simple. You all know, right? Minimizing the sum of square errors to find this, to search for the best fitting parameters, or maximum likelihood estimation, which allows you to assume different error structures. So if you want to use Poisson error structure, or normal or negative binomial error structure, works well with over dispersed data, you can apply maximum likelihood estimation. And on the left, you have the example with Poisson, you know, data with Poisson. And on the right, you have same data with negative binomial error structure. You see how more dispersed is, right? So you can specify these error structures in the toolbox. That's the good thing. And then to estimate the uncertainty of the parameters, we employ what we call parametric bootstrapping. So once you feed the model to the data, you produce more data sets by bootstrapping. How do you do that? Well, you simulate the error structure on top of the best fit curve. So whether that error structure is Poisson or negative binomial, you can simulate it and then repeat that 300 times so that you have about 300 bootstraps. And by the way, everything is explained in the tutorial paper if you're interested in looking more closely. And then from each of those simulations, you refit the model and estimate the parameters so that you have now a new empirical distribution of parameters. And that's how we obtain the uncertainty. So the confidence intervals and all that. So here's an example with, just to show you how things change with only 5 replications or 5 bootstraps is very small, right? With 10 bootstraps, 100 and 300, you see, you need about 300 realizations of bootstraps to get this nice bell-shaped curve in the empirical distribution, in the empirical distribution of the parameters. That's what you want, because from that empirical distribution, then you get the range of the parameter, beta, you can get the confidence interval. Now, the nice thing about this approach is that because you did 300 bootstrap realizations, basically you have 300 fits. And from each of those feeds to the data, you can extrapolate or project forward in time to generate a prediction into the future. So basically what you're doing is moving time forward h units, where h is what we call the forecasting horizon. So how far into the future we want to predict. That is the forecasting horizon. And here is an illustration of that, right? So everything that is prior to the vertical line, that's the calibration phase. And everything that is on the right is the prediction phase obtained by extrapolating forward in time, h units. And here's an example of the model fits. This is just model fitting to the Spanish flu in San Francisco. This is a data set that we have used many times in our work. Just showing you how the fits look like with different numbers of bootstrap realizations. So it's just fitting the first 18 data points. It's the early exponential growth phase, as you know. Now, the next thing is, how do we assess how well the models fit the data, right? And this is something that you have done with error metrics in your own work. You have the mean absolute error, the mean squared error. So these are measures of error, measuring how far is the model fit to the actual data. There are 2 other measures that are very popular now in forecasting work. One is the weighted interval score. It's a nice measure because it's accounting for the full probability distribution of the model fit. Because remember, the model fit, right, is just the median, the one curve. But in reality, you have an uncertainty around that. You have a distribution. So if you assess how close that full distribution is to the data, in order to do that, you can use the weighted interval score. The weighted interval score will penalize data points that are far away from that distribution. And a first approximation of the weighted interval score is just the 95% prediction interval coverage, because this prediction coverage is counting, right? How many data points are located inside the 95% prediction interval. And so these metrics are coded in the toolbox, so you can get them right away. You can get them not only for the calibration phase of the fit, but also for the forecast. You can obtain them. You can get them for the forecast if you have the data, right, for that forecast to be able to evaluate that. So here's an example of that. So you see, this is the fit to the first 18 data points left of the vertical line. And then the forecast is on the right.
Thank you very much, Ma.
Right. So you see the forecast here shown here on the right of the vertical line is actually pretty good, showing that many of the data points, which are the blue circles, are close to the curve, right? And then the metrics on the right are the metrics that I show you, and they are a function of the forecasting horizon. So, you know, as you go far into the future, right, the error will tend to be bigger simply because you have you are accumulating those errors. Okay. So here's another example of a full workflow analyzing the early wave of COVID in Spain, right? So you see here, we are using a very simple growth model, which is a generalized growth model. You may be familiar with it. It's a simple model, 2 parameters, the growth rate, the deceleration of growth or the scaling of growth parameter P. So if P equals 1, then we have exponential growth, right? If P equals 1, this equation is Malthus, right? This is exponential growth. But if P is less than 1, this is more like a sub-exponential growth, something more like polynomial growth. So for this example of the Spanish flu, P is 0.93 on average, but the confidence interval is actually nearing 1. So it's not too far from 1, close to exponential. So the next step is to use, let's use a mechanistic model, right? Because we want to say something about the disease, something about the transmission process. Let's measure the transmission rate beta and the proportion of reporting, the reporting proportion. So if we try to fit this model, the SIR model with underreporting, remember that the underreporting parameter is rho, it's a proportion between 0 and 1. We see that the beta parameter is well identified because, you know, it's quite narrow. The confidence interval goes from 1.6 to 1.9. It's a little skewed to the right. Notice that. But the reporting proportion, the uncertainty is much larger. Notice that it goes from this area here in 0.3 to all the way to 1. Tends to be concentrated around 1 because that's why the mean is 1. But the uncertainty is quite broad. So in this situation, we would say that the parameter is not quite practically identifiable because the uncertainty is too large, right? That's one way to conclude. So in that situation, what you could do is say, okay, however, you know, the mean is 1. So what if we just assume that the reporting proportion is 1, meaning that everything is observed? So that could be one way to go about this. And if we do that, that means that we will use a simple SEIR model. Notice how the uncertainty of beta is reduced. It used to be between 1.6 and 1.9, the confidence interval. But now that we only have one parameter, we are not estimating rho, the uncertainty is quite tight. You know, it's between 1.6 and 1.6. The good news is that the model fits well the data still, right? That's important because if the model doesn't fit the data, then we cannot continue. We have to find a model that fits well the data. So that's for the early growth phase. Now, as the epidemic goes over time and interventions are put in place, then we need to account for this in the model, and we can do that by assuming a time-dependent transmission rate. Like in this case, the transmission rate has, we set it up with this exponential form. You know, that means that the exponential is has a rate Q. That's how fast the intervention is put in place or the behavior change is put in place. And that's illustrated in this graph on the right. So it starts constant. Once the intervention is put in place, which is represented by the vertical line, there's an exponential decline. And then that exponential will find a low level was the second level beta 1. So that it's a change from beta 0 to beta 1. That's what we are modeling here. And look at the model fit. The model with this structure fits the data very well for
Okay.
the models fit the data very well, right? And see how the parameters are also well identified. And how do we conclude that the parameters are well identified? Well, you know that the uncertainty is quite tight. Look at the empirical distribution of beta 0, beta 1, alpha, Q, and rho. They are very well identified. There is no broad uncertainty, so that's good news. And maybe not that surprising because as you have more data during the course of the epidemic, then you have more information to be able to characterize the other parameter. Now that we have a model that can work well with later phases of the epidemic, we can test it in real time. Let's generate some sequential forecasts as the epidemic evolves. And so what I'm showing you here are 45 day ahead forecasts, moving from this panel with 30 days of data. So again, the vertical line separates calibration from prediction. 35 days, 40 days, 45, 50, 55 days. So you see that at the beginning, when we only have data about the early growth phase, it is difficult to predict when this is going to peak. And that's essentially because we don't have that information to know when the information about the intervention, right? It's later until the epidemic is slowing down that we can start to infer the impact of the intervention. And in this table, you see the errors that are summarized. Obviously, when you have only 30 days of data, the forecasting error will be huge because it's assuming that everything is growing almost exponentially. But notice that once you reach the peak, the epidemic is doing a good job in forecasting. The uncertainty in the forecast is including the data points. And these are long forecasts, right? So these are 40-day ahead predictions. Anyway, so that's what I wanted to show you as a way of summary. I talked about structural identifiability, practical identifiability, the importance of this. I show you a few examples of how to do this using some methods, and I noted a couple of tutorials that can be useful for this. I also highlighted the importance of specifying the error structure and that the error structure can impact the quality of the prediction. And then finally, I also show you about the toolboxes that we are using to generate practical identifiability. And yeah, obviously, this highlights the importance of collaborating with mathematicians, public health scientists, epidemiologists, to bring together the whole thing to be able to move forward the field of epidemic forecasting. And I don't have a lot of time, but I also wanted to mention about Bayesian fit forecast, which is this toolbox that I developed with my student Hamed Karami, and it's the tutorial will be published in BMC Medical Informatics and Decision Making, and the GitHub site is there. We continue to improve the toolboxes. They are not perfect, but they work very well now. I think they are stable versions now, and I'm happy to provide you support in case you need them, you need to use them, and thank you very much for the invitation.
Some modeling.
Yeah, yeah, that's the education.
Are there any questions? Are there any questions for me, or everything was okay, clear?
No, I think it's the noise. No, it's something that
So thank you very much, Professor Gerardo. Can we give him a round of applause?
Thank you.
So yeah, I don't know if there are questions here. Questions.
Yeah. If you have questions, happy to take.
Then online participants, can you type your questions if you want, or you indicate that?
Yes. Yeah, maybe typing, but yeah.
Thank you, Prof, for the presentation. Thank you, Prof, for the presentation.
Thank you.
It's valedictory, but there are some questions I want to find out or I want to ask. From the second to the last part of your presentation, I don't know if you can. Can we move the? I mean, can you come forward? Okay. Can you hear me?
Yes, I can hear you. Yes.
Okay.
Please,
So,
please.
Go on. Okay. I want to see the slide on the second to the last part of on the graph there. I'm trying to understand something.
Okay, slide 20.
The
Which
second
one?
to the last part.
Second to the last.
Second to last. Okay. That one or this one?
No, before this.
Before this one, yes.
Okay, from this, the next one.
This one?
The next
Next one?
we have 40, I think 30 days, 40 days, 5 days.
After this, okay, fine.
Okay.
Oh no, yeah. Oh, sequential forecast. Sequential forecast.
Before this, okay.
Thank you.
I'm trying to look at the graph here because when you say 30 days, you say 45 days ahead forecast, and you consider the one of 30 days, 40 days, 45 days, 50 days, and
I'm sorry, what was I didn't hear well. Can you please repeat the question?
what I want to find out from this is it the same data or the same data that you use here? Because I'm seeing different, or you change the number of days that you change here. Not the one that affected the.
Okay. Yes. So what's changing here? Yeah, that's a good. What is changing here is the amount of data, right? So it's the same model, obviously, but what we are doing here is feeding an increasing number of data points. So we start feeding first 30 data points only, right? And that means you feed the model and then generate the prediction, and then feed it again using 35 data points, generate the prediction, and then feed it again with 40 data points, then with 45, 50, and 55. So every time that we increase the amount of data, you need to repeat the inference process, the fitting process. Okay, and that means that the parameters are changing, right? The estimates will be changing. I'm not showing you here the parameters how they are changing. In the previous slide, I show you the estimates of the parameters here, but that only for the full data, right? For the full wave, the first wave of COVID in Spain, right?
Okay, thank you so much. Then the
Thank
second
you.
question is from the table. There is a table that you showed also, where you show basic reproduction number and the rest. For this.
Right. That's a great point. I didn't include the reproduction number. That's yeah, you're right. I didn't include it, but the reproduction number for this, it was around 3 to 4. But you're right. And that's only estimated from the early phase, right? When there's this exponential growth phase. I didn't show it because the focus was more on the forecast, but you're right, and can be estimated from the ratio of beta divided by gamma. Right. So the estimate of beta divided by gamma can give you the estimate of R0.
Thank you.
Thank you very much.
Thank you very much, Prof, for wonderful presentation. So I have some questions based maybe a bit out of the scope of what was discussed because of the nature of the data, this particularly, but some of the things you presented. So I wanted to ask if there is shed more light on how you can make inferences from cross-sectional data with a dynamical model like we have normal D models.
Sorry, what type of data you said?
So his question is that you have made use of incidents, but now how can you also use this for cross-sectional data? Like instance in time, data collected in time.
Yes. Okay. So cross-sectional, in the sense that there's only one time point.
Yeah.
Yes. So it's not time evolution is maybe age or other things.
Okay. Right. Yes. Let's see. That's a good point. You could. So let's say, for instance, you have seroprevalence data, right?
Yeah.
At a given point in time. So that means that your data will consist of basically one single data curve. You could assume, right, that the previous time points was an increasing function to that, because seroprevalence is a monotonical increasing function, right? It's increasing as the epidemic evolves. So you can make some assumption about how that growth happened, and then impute the growth phase all the way to the data point that you have in the cross-sectional data, and then fit the model to that. That's what I would do, because having a single data point is not going to work, right? You need to have a way of assuming, for instance, that the growth to that seroprevalence level, let's say whatever that is, 50%, follows some sort of shape, maybe logistic, right?
All right, Prof. Is there probably a paper or a resource you think could be helpful regarding that could strengthen some of the ideas you just shared?
Yeah, I'm happy to communicate with you and others, and I can send you some paper. Right? Yeah, sure. I can look for it. I can look for a paper that could help you in that regard, and yeah, if you write to me, I will be happy to communicate and see if that's what you were thinking and help. Yeah, definitely. I would be happy to. Thank you.
So thanks so much, Prof, for presentation.
Thank you. Thank you, Dr. Bakari. It has been a pleasure. Thank you so much, and we'll be in touch. Yeah.
Yeah, not finished.
So this is another question.
Another question.
One more question. Okay, sure.
Other questions.
There are still more questions. So
you don't change my thing. Yeah.
Hello, Prof, can you hear me?
I can hear you, but
Okay.
not the question.
Let me just please say that there are still more questions. So I just want to ask my question now. There are still other people who have questions to ask.
Okay.
Okay, so now currently I'm doing a malaria walk where I incorporate climate variable, temperature specifically. So and I'm carrying out a model fitting using ML. Can I continue?
Yes. Yes.
Okay, so I'm using MLE for the model fitting. Okay, so I'm using MLE for the model fitting. So we're trying to quantify the uncertainty associated with the parameters to be estimated. I've been encountering an issue with one of the parameters where while the uncertainty is quantified for some of the parameters, but one of the parameters is just bring out NA, that is not available, not available. So, and I've tried to do that quite a number of times. I'm still getting the same thing when it comes to that particular parameter. So I want to really know what could be the problem that is causing that. Yeah.
Okay. That's a great question. How about if you could share with me the output so that I can take a look? Share with me in an email and then tell me when you are getting that error. I will be happy to advise. Okay. So yeah, maybe there's something in the way that the thing was specified in the model. But yeah, please share with me the details and I'll be happy to check for you, okay? And I have a question for you. Since you are doing the malaria model, do you do identifiability? So you're doing identifiability, right? As well?
I'm just saying it's more clearly than probably the system.
Okay. Sorry, I didn't hear very well the response. But what I suggest is if you can send me an email and I will review the issue and I'll try to troubleshoot the issue with you. Okay? Thank you so much.
Thank you, Professor Drew. Presentation. My first question I want to request, I don't know if you can, if your slide is available, will it be available for us?
Yes,
Thank
I'm
you.
happy to share with you. Yes, I will send you by email. All right? Definitely. I can see that after the.
So my second question is on structural identifiability. You show that without initial conditions, we are just about just few parameters that are identifiable, while with initial conditions, almost all or all of the parameters are. So I'm just wondering, what instances I have that will have a model without initial conditions, except say for mathematical exercises. Yeah. So
yes, right. The thing is, right. So the initial conditions represent information, right? And basically, when you know the initial conditions, you are constraining this the parameter space and the model space to specific values, right? Because if you don't specify it, so it's a huge dimensional space. But if you fix the initial conditions, you are constraining a lot the potential set of solutions. It tends to help a lot constrain the model, and that will help you improve the identifiability. For that reason, that is just more information, and you're constraining the model.
Thank you.
Thank you.
Okay. Yeah. Thank you so much for your presentation. I have quite a number of questions here on things that have been bothering me for some time. So now, but first going through the issue of practical identifiability, which you showed that we could use the density plots of the posterior distribution, of checking that to see if it's so wide, then we can say that
it is the parameter of a certain parameter is not practically identifiable. Now, so I want to confirm that that was what you were actually saying, that you could use the density plot of the posterior distribution of the estimated parameter. That's one thing. I also saw that while you were trying to correct the issue of the practical unidentifiability of that parameter, you went on using more realistic transmission function, which is the piecewise transmission rate over time. Now, I want to know, is that the only way? And now, that is now going to lead me to the third question, which I said has really been of interest to me for some time now. I went through one of your papers where you were talking about different costing function, where you talk about costing function, where you talk about using temperature, I think temperature, and then the other time you talk of using, I think something like Fourier and all of that. And in these three costing functions, the one that this Fourier kind was able to capture fits the data better, but you also made a comment that after the prediction, after the calibration interval, we'll not be able to use that one again. But you were now trying to compare between the sinusoidal function and that of use of temperature. So now when I saw that you used this issue of piecewise transmission rates to better the fits that we got in this last one, I was now asking that, okay, coming to forcing function, how do we determine the forcing function to use? Particularly, I've been working with some data sets that irregularly fluctuates. They don't have regular patterns like that. A lot of noise all around. So what is the best way to choose the forcing function to ensure that the model fits properly to get a good fit? So, so in general, so what's your advice? Thank you.
Yeah, those are great questions. So the first one about the posterior distribution to assess the uncertainty, right, of the parameters. In the frequentist approach that we use with quantitative forecast, it is not called the posterior, right? Because it's not Bayesian. It's not a Bayesian approach. So it's just the empirical distribution of the parameters that we obtained. But when we use Bayesian fit forecast, which gives you the Bayesian parameter estimation approach, you are right. That's the posterior distribution, and from the posterior distribution, you can extract the 95% confidence interval. So you are right. So that's what you use to assess the uncertainty and determine if the parameter is well practically identified or not. If the uncertainty is too large, then it's not well identified practically. Okay, so that's as far as the first question. Now, the second question was about the function that we used for the transmission rate. So that function, let me share back that function is an exponential indeed. And my experience is that this function works pretty well for many epidemics, whether that's Ebola or influenza. This exponential piecewise function works pretty well. There are other variations of this type of functions that have been used as well in the literature. For instance, you can think of not an exponential decline, but a power law decline instead. That's something that you could try as well. Instead of having the exponential, you can have 1 over time and then to the power of something, to the power of q. But overall, this works pretty well in my experience with few outbreaks, feeding models to data. This exponential decline function works nicely. So definitely I recommend trying this function first whenever you have a need to characterize transmission rates. The other question you asked was about whether there's another way of doing this, and the answer is yes. So you could use non-parametric approaches like spline, right? You can, instead of assuming a specific function parametric form like this, you can use splines to fit the model and generate forecast. So that's a non-parametric approach. And that's something that my colleague at Georgia State, Alejandra Smirnova, has done it. And we have a couple of papers using that type of non-parametric approach. I can share those papers. One of the papers is in infectious disease modeling, and one I think is in an inverse problems journal. So that will be an example of non-parametric approach to fitting changing transmission rates, so time-dependent transmission rates. And then, so you asked me for other functions, right? Other functions that could help you characterize the transmission rate that could be linked to real data, such as temperature. And the answer is yes. You could link it to specific signals, external signals, such as, mobility changes. If the mobility change and the population changes because of a lockdown, substantial social distancing interventions, that information can be obtained from things like Google mobility indicators or the Google Mobility Index. And so you can grab that information and then use it directly into the beta and then affect it directly. So yes, so basically I just described three ways, right? This is the parametric form. There is another form using non-parametric splines. And there's the third form, which is connecting the change of beta to changes in populations, mobility, and behaviors. I have a paper back in 2010, where we linked the frequency of TV viewing in the population of Mexico. Once, in Mexico, the pandemic started, the H1N1 pandemic started, the whole thing, right? And then they closed the schools nationwide, so there was a major lockdown. So we obtained information about the frequency of TV viewing from some survey company, and then we link it to the model, and we were able to characterize the shape of the epidemic. And so that's a paper that we published in BMC Infectious Diseases. So I'm happy to share with you as an example of that type of approach. Yeah.
Yeah, I want to read something there because most of the disease most of the disease you have looked at, you have used this probably epidemic and the outbreaks. And for malaria data, there's an endemic. It's endemic, and it gets data from the public airspace, which ranges over a long period of time. And you also find out that for a malaria model or vector bone like, where you have the mosquito and then the human. So find some kind of difficulty. It's always easier for outbreaks. Most of this assertion, when it comes to dealing with endemic models, it's always quite very difficult. That you may need to try different things before you come up with the optimal result.
That's exactly right. Typically, modeling is an art, right? So there is no specific recipe all the time. You need to try every data set is different. And sometimes one thing works, and we know we have a hunch based on experience of what type of model and what type of mechanistic approach can work. But every problem is different, and sometimes you need to come up with new solutions and in a way that also brings novelty into the work, right, that we do.
Okay, so following up from what Prof just said now, so the question I was asking has to do with like this paper, you published with Ahmed on parameter estimation and forecasting strategy for cholera dynamics.
Yes.
Yeah. So
yes.
in that paper, okay, so in that paper, you use 3 forcing functions to discuss the good, how the model fits the data based on the forcing function used. So there were 3 forcing functions that were talked about. You talked about one, the sinusoidal function. Then you talked about using, if we use rain, I think temperature as a driver. And then the other one, you used this data-driven time-dependent transmission. Yeah, so those were the 3 approaches you used. But for the third one, which is the data-driven time-dependent transmission, the model fits data very well. But you also made a comment that after the calibration interval, that it does not do well after the calibration interval. So you further had to now use compare the result between the sinusoidal function and the one with the temperature as driver. Now, I'm working on malaria. I'm interested in actually predicting after my fitting. But the data is messy, is noisy. Data doesn't have a regular, punctuation like that. Punctuates irregularly. Now, using either sinusoidal function is not capturing it well because it's not regular. And then thinking of a driver as well, maybe temperature or rainfall, also it's not giving the exact, but it's not giving the capturing also very well. Now, if I have to, so what's your suggestion now about choosing a forcing function that can balance between model fitting and prediction at the same time, that I can use for predicting
right
after the calibration process? So that's the question I said has been bothering me. And then having the data being noisy, and then this is malaria model. Right. Thank you, sir.
Yeah, you're right. So and that's a very interesting paper that actually we published recently, right? With my student Hamed Karami and with the colleague that I mentioned, Georgia State, Alejandra Smirnova. And by the way, I think Hamed would be happy to give a talk about the cholera models. If you want in the future, just let us know. He can go into the details of that paper. So to answer that question, you are absolutely right when you say that, you have different ways of characterizing the transmission for cholera. And that paper is an example of, trying different things and testing them and see which one works better. And sometimes a model that fits well the data doesn't mean that it will predict well. So it's not clear cut. So the best way of assessing this is to do multiple calibrations. So not only one calibration, but you calibrate as the epidemic evolves, as in the example that I show you in my slides, when you had 30 days of fitting, 35, 40, 45, 50, you do multiple fittings, and for each of them, you do a forecast. So from that, you can get the average of the forecasting performance and then compare different models or different ways of, different ways of characterizing the force of infection. Because a single prediction doesn't mean anything really, right? The model could have predicted well by chance because it's just one. But if you do multiple of them, it's more likely that you will be measuring how well the model performs. So yes, my recommendation is to use multiple calibration periods so that out of that you can gather information about how well one approach or another works. And yeah, if you want at some point to invite one of my colleagues to speak specifically about the cholera modeling, I think that would be great. Yeah, and then we can continue that discussion, and we will be happy to help you. If you think that approach of fitting could work well for the malaria and you want to try it, I think there's an opportunity also to share some code with you if you want and try some of those approaches. So, yeah. Thank you. Great questions. And by the way, I have a
Thank you very much for the presentation. I want to know, at what point can we introduce the reporting rate? Because you talked about maybe checking the reporting rate if it's up to like 0.99, which means the model actually capture reality. So I'm like wondering, at what point is it necessary? So that's my first question. So I want to know the reasonable performance metrics that models should have, because looking at the forecast statistics that you showed, we have different values. So it's big skeptical to know what is the reasonable metric that a model should have, and is it of the forecast or the test string? Because I'm seeing that you did it on the forecast, so I want to know the reason why. And you also talked about bootstrapping, and it's very computing intensive. So is there no other method that one can check for the uncertainty?
yeah.
Aside
Okay.
variation.
Yes.
That's my question.
Yeah. No, those are great questions. I think the first question was about the forecasting performance, right? So the metrics that we use for forecasting performance, right? Sorry.
The reporting rate. I started with reporting rate. Is it necessary we add in, at what point should we add the reporting rate? Is it
Okay.
necessary to put it in whole model?
The reporting rate parameter is important if you want to do some inference about what fraction of the cases are being reported in the surveillance system. So that's one way we do it, right? Adding just one parameter. Obviously, that's just assuming something very specific. For instance, it's assuming that the reporting is constant throughout the period of the epidemic. It doesn't catch any potential changes of reporting over time. So it's a little tricky. So you can interpret that as an average reporting, and it works. It works when for the simple questions of what is the reporting rate? Am I catching 5% of the cases or 20% of the cases? And this was one of the questions that was asked quite a bit during the early COVID-19 pandemic in early 2020, in March, April 2020. So that works. And then regarding the computational intensive approach of bootstrapping, yes, it can be intensive, but with the current computers, things are not too bad because you typically need 300 bootstraps. And if your model has just a few parameters, a few equations, you can complete that process in a few minutes, typically on a decent computer, right? Now, the other approach is the Bayesian approach, but the Bayesian approach relies on a Monte Carlo chain, right? MCMC. Monte Carlo Markov chain sampling, right? And that can be intensive, even more intensive than bootstrapping in my experience, because sometimes you need to do this sampling for 100,000 iterations to be able to make sure that the parameters converge. And in my experience, that can take hours, and sometimes it could be days, depending on the complexity. Especially if you're looking for convergence, to be sure that you ensure that the parameters are converging to their stationary values, and you want to get the R hat metric of convergence below 1.1. So yes, bootstrapping can be also intensive, but my recommendation is to use 300 to 500 iterations. And that typically, that typically doesn't take more than a few minutes, I would say, in my experience.
It remains the performance metrics. The performance metrics. It remains the performance metrics. What's the reasonable performance metric that the model should have? Because we're looking at the forecasting metrics, I saw different values. So what is the reasonable metric value that you should have? The value, because I'm seeing larger value. So I'm even seeing 600 and something. So what's the reasonable metric value that the model should have?
The values of the forecasting performance metrics, so they will vary depending on your data, right? The important thing here for the forecasting performance metrics is that you use them for comparison. You use them to compare one model with another, right? That's the thing. That's the way you can say, oh, this model is forecasting better than model B, because you are comparing them. If one model is giving you lower errors, lower MAE, MSE, and WAS, then you say, oh, it's giving me better performance than this model. So they are useful when you have multiple models for comparison. The coverage of the 95% prediction interval is also useful by itself, if you want to say something about calibration. If the coverage of the 95% prediction interval is close to 95, then you say that the model is well calibrated. That's probably the only metric that you can make a statement. And of course, it's not only about the metric, but also about the visualization, right? How does the model fit looks like? Is it really close to the data, or maybe you have systematic changes, etc. Yeah, I'm sorry, but I'm gonna have to leave because I have a meeting soon.
I appreciate you.
Yeah,
So
let's continue over email, okay? And we'll be in touch. Thank you. Thank you very much. Okay, we'll be in touch. Bye-bye.
Tell them we're sorry.
Question about check the question.
Okay, sir. Okay, please.
Starting from one, which member of what?
Open it.
Okay.